Greetings to my fellow ComNet colleagues. Thank you for this opportunity to present to the Symposium on Innovations and Collaborations about a novel concept to connect Antarctica to the global subsea telecommunications infrastructure and, in the process, enable science at the same time. So this is what NSF is proposing. Depicted in the top graphic, the National Science Foundation is investigating the following: the implementation of a modern subsea fiber optic telecommunications cable interconnecting the US McMurdo Station with either New Zealand or Australia to provide advanced high-speed, low-delay telecommunications. A cable designed to double as a science research sensor and a platform to connect sensors by instrumenting the cable with science sensors incorporated into the cable telecommunications repeaters, providing additional fiber optic strands dedicated as a science sensor, and to provide connection points on the cable's path for future science cabled observatories or other instruments supported by the cable's power and telecommunications. To understand some of these concepts, background on the proposed science sensor technology is needed for a frame of reference. Depicted in the bottom graphic is a representation of an embedded science sensor to be incorporated into the cable termed SMART, which is an acronym for Science, Monitoring, and Reliable Telecommunications. The United Nations International Ocean Commission UNESCO organization Joint Task Force on SMART has been promoting the concept of instrumenting the world's oceans as new subsea telecommunications cables are deployed. Presently, there are 522 cables installed or planned in all ocean regions, including the high Arctic, but none in the Antarctic. The basic concept calls for incorporating temperature, pressure, and 3-axis acceleration sensors into standard telecommunications repeaters and tapping the cable's power and communications. The SMART concept calls for a keep it simple and do no harm to the telecommunications functions of the cable. Also included in the cable concept is the addition of extra fiber optic strands dedicated for a sensing technique termed distributed fiber sensing. In its simplest form, distributed fiber sensing uses a shore-based laser to send pulses of light into a dedicated fiber optic strand that measures the return reflections from tiny scattering points along the length of the cable, typically at distances up to 100 kilometers. Data analysis enables extraction of useful seismic data, marine animal sounds, and temperature changes along the path of the cable. This turns the cable into a very long sensor that is not practical using conventional instrumentation approaches. The motivation for the telecommunications is this: there is a need for enhanced telecom capability, bandwidth, and low latency for cross-cutting support to science research and the operational logistics and human well-being required to support that research. McMurdo Station is a large, logistically complex science town with populations ranging from low hundreds in the winter to 1,000 in the summer, yet it does not have bandwidth of a single U.S. average household of 2.5 people. The graphic on the left is a statistical statement of the reality of supporting 1,000 people in this manner. The network is oversubscribed or congested, despite the best efforts by our network engineers to manage usage priority and unnecessary bandwidth-hungry applications. The bandwidth capacity of the cable is measured in increments of 100 gigabits per second, which is orders of magnitude greater than McMurdo's present 42 megabits per second. Thus, the cable represents essentially an infinite capacity. The cable can interconnect with the international network of high-speed national research and education networks in the Pacific, or also known as NRENs, as shown in the graphic on the right. This will connect McMurdo with universities and research organizations worldwide at high speed and low delay. The motivation for the science is this. The Southern Ocean has been described as one of the most underobserved areas of the global ocean. More is known about the surface of the moon than the vast expanses of the Earth's oceans. The Southern Ocean is remote, experiences harsh weather, is largely inaccessible for large fractions of the year due to sea ice cover, and it must be accessed by research vessels that are limited in number and typically in high demand. Visualized in the upper graphic, the Antarctic circumpolar current is the largest component of the global ocean circulation system, and it has important contributions for such factors as the absorption and transport of heat, the sink and distribution of carbon dioxide, and the upwelling of nutrients that affect bioproductivity, such as ocean fish stocks for the global food supply. Visualized in the lower graphic, the seabed south of Australia, New Zealand is a very active seismic area where the Australian, Antarctic, and Pacific tectonic plates interface. The Macquarie Ridge Complex and associated Pusager subduction zone, which are traced by the concentration of earthquakes depicted, are of high interest for understanding tectonic plate subduction processes, and also for the potential for tsunami generation, which is of economic and societal risk importance to the southern New Zealand and Southeast Australian coasts. The efforts to date are these. In late June of 2021, NSF supported a research community science workshop to review the science benefits of such a cable, summarized in the graphic on the left. In its final report, the workshop stated 4 findings. Finding 1, existing and future Antarctic research would be significantly enhanced if bandwidth limitations were eliminated through the availability of a modern submarine cable system. Finding 2, a new submarine cable could be constructed with embedded instrumentation, such as SMART, that would itself enable meaningful new research and understanding of the region. Finding 3, robust bandwidth for interpersonal connectivity for scientists and staff, if thoughtfully approached, could be transformative for research and work functions, particularly in Antarctic science, education, engagement with the public, and community well-being. And finding 4, construction of a new smart cable that provides essentially unlimited bandwidth to McMurdo is feasible and could also serve as a platform to extend connectivity to deep field research sites as well as critical research programs at Amundsen Scott South Pole Station. This level of connectivity can transform the science and research platforms for future generations. Signified by the graphic on the right, in response to the science workshop, NSF contracted an industry-standard preliminary concept feasibility study, also known as a desktop study, which incorporated the unique attributes of implementing a cable to Antarctica. The final study report is comprehensive in scope and depth and represents approximately 9 gigabytes of digital information, including significant geographic information system digital files. The study addressed 2 proposed routes for comparison: McMurdo Station to Sydney, Australia, and McMurdo Station to Invercargill, New Zealand. Brief assessments of optional extensions from the main cable routes to Macquarie Island and to the Terra Nova Bay area were included for any future interest of national Antarctic programs. Maximum use of available open source information in the form of geographic information system data, research science data holdings, such as the standard general bathymetric chart of the oceans, Antarctic region science research publications, reviews of environmental permitting laws and regulations, interviews with subject matter experts, and engagement with the science research community and discussions with the cable supplier operator industry were conducted. The potential for incorporating smart repeaters and distributed fiber sensing science sensors was also addressed. The study is comprehensive and detailed, hence these are just a summary of the notable results. The table at left summarizes the key parameters evaluated by the study by comparison of the two routes considered. For brevity, a few key points learned are here. Both the Australia and New Zealand routes are considered technically feasible. The New Zealand route is favored over the Australian route for the following reasons. The New Zealand route is 1,500 kilometers shorter and thus more economical. The Australian route has additional geophysical risk to the cable, and the New Zealand route covers more regions of science interest. Optional branches for the routes to Macquarie Island and Terra Nova Bay were initially scoped for potential follow-up, should any national Antarctic program show interest. The cable route has interest of seismologists who propose to have cable branching units located at 60 degrees south and 50 degrees south for future sea bottom seismometer instruments, which will tap the cable's power and communications capability. The route requires finding a relatively safe crossing of the seismically active Antarctic-Pacific tectonic plate boundary, which takes it to the east after descending from the Antarctic continental shelf. The risk from ice scour appears reasonable, which can be mitigated at the McMurdo cable landing using standard subsea cable landing techniques. Routing of the cable onshore at McMurdo has two suggested paths to enable the cable to follow existing elevated utility runs from the shoreline to potentially house cable landing station equipment in the new data center, which is now nearing completion. Of particular note, the study identified the need for coordination with the Committee for the Conservation of Antarctic Marine Living Resources, or CAMLR, as the proposed cable route transits the CAMLR-governed marine protected areas in the Ross Sea region. And finally, environmental assessments and permitting will be significant, as is the case with all subsea cable projects, and will include the Antarctic Treaty Committee on Environmental Protection Protocols. Thus far, however, nothing has been noted that is out of the ordinary for a subsea cable project. Here are highlights of NSF's future plans for next steps. The preparation and release of a public edition of the desktop study, which would be of interest for national Antarctic programs, the science research community, and the subsea cable industry communities. Additional short-term studies for more understanding of points raised by the desktop study, such as ice scour risk by icebergs, sea ice cover open periods for cable ship access, market research outreach to the cable industry suppliers, and a construct of detailed requirements needed for proceeding with environmental reviews and permitting. A continued assessment of technology development for science sensor technology, particularly for smart telecom repeaters. Additional engagements with the science research community to refine the cable route. This will optimize science research objectives in balance with geohazard risk to the cable. And planning for a future detailed bathymetric and seabed geophysical survey along the proposed route, called a marine route survey. This will be required to finalize the cable route and provide essential data needed to feed expected environmental and permitting reviews. Requirements planning will include identification of suitable vessels with necessary precision multi-beam bathymetric sonar capability. In conclusion, there is strong scientific rationale for the cable. Transformational scientific telecommunications enables innovation in science research by access to modern academic research tools, to include high-speed networks, remote data repositories, rapid transport of data from the field to the home institution, and high-performance computing supporting artificial intelligence and machine learning that is pushing the frontiers of big data, such as distributed fiber sensing and science research supported by the cable sensors has societal relevance on a global scale for filling knowledge gaps of key ocean processes and trends for improved understanding and monitoring climate change, for such things as ocean heat transport, carbon dioxide sequestration, and sea level rise. Technically, the cable appears feasible. The two routes evaluated are technically feasible, with the route to New Zealand found to have clear advantages due to shorter length and greater coverage of science research interests. There are no immediate technical risks identified from the Antarctic unique section of the cables, such as ice scour, but more study is warranted. The incorporation of science sensors appears to be viable for both dedicated fiber optic strands for established distributed fiber sensing and the promising development of smart telecommunications repeaters. Thus, NSF will continue additional studies to further refine understanding of potential risks and risk mitigations and prepare for the next phase of effort, which will be organizing the environmental evaluation process and planning for a marine route survey to examine the seabed of the cable route in detail. Thank you, and this concludes my presentation.